as a definition. I think there are other ways of characterizing.
Yes, sure.
Oh, okay, yeah. But yeah. Let us take this as the definition. Yeah. And so to check that this is the case, well, we want only to show them that for let's see, sigma in this space, that
it annihilates all our L.
yeah, that right, yeah, that for a sigma here, that any anti-holomorphic that when we take the interior product, and that's why I didn't want to erase that up there, that when we take the interior product of an anti-holomorphic element in the complexification of V with the top level of a holomorph with this, then, well, that is basically another characterization of, I mean, the fact that that goes to zero is basically another characterization of what it means to be in the holomorphic space, or the holomorphic subspace of the complexification of V dual. So okay, for all little v in V 1, 0, it's true that.
So I'm lost. Your sigma is the rho in that formula, right? So maybe we can call it rho instead of sigma.
Okay. Oh yeah. Thank you. Yeah.
Because why is this line for some rho?
What do you mean? Yeah.
Why is this thing is canonical line?
That's what we're that's what we're about.
It's a question about dimension.
Yes, about dimension.
How do we know that it is a line?
Yes.
Well, we can appeal to the fact before which asserts that if there's that.
How I think about that? Indeed, n is the dimension of V, right?
N is the real dimension of V. Yes.
Yes, and then when you take this V star, it's again of dimension n. And when you take, but it's kind of a real dimension to n, but complex dimension n, because here we also take complexification. Then we take just one half of it. You take eigen space of I. Then it's again of dimension n. And when you take n's exterior power of n dimension of a space, you have a line. That's somehow.
It's the top exterior power. It's the nth exterior power of
you have a
n-dimensional
two-dimensional vector space generated by E and E1 and E2. Then its second exterior power is generated by E1 wedge E2, just one generator, because all the others are zeros.
Yeah.
E1 wedge E1 is 0, E2 wedge E3 is 0, and so on.
Yeah. So actually, this is where I think the terminology canonical line comes from, because this is the canonical line in complex geometry. So
it's canonical line bundle.
exactly. Yeah. Right. Yeah. This is the canonical line, which is the fiber of the canonical line bundle in complex geometry. Yeah. So this is the motivating example, I guess. Okay, so if we have V in the holomorphic subspace of the complexification of V, and we have a rho in let's see, V dual 0, 1, then interior product, then the pairing of V and rho, or I don't even have to write interior product, rho of V equals 0. That is, I think sometimes the anti-holomorphic subspace of the complexification of a dual is sometimes defined, I believe it's sometimes even defined to be the basically the annihilator of the of the holomorphic subspace of on V and vice versa.
But what is the point
Of what?
of this line?
You mean what are we going to do with it? Why are we considering this?
Yeah.
I don't know.
Okay.
But an entire section is devoted in Caviel, in the other reference that we're using. Actually, so this material, this material here, is from our primary reference.
Okay, so I was expecting that we should prove that rho is when acted upon by L is 0.
That's what. Yeah, I mean, so
Because this is not L, right?
so
Evident, you just develop all the definitions, I think, because you have there's two parts of space L, and the first part acts on it trivially because it's just the same forms.
yeah, that's
Take
right.
like action of dx times dx divided by
Right.
something.
Okay.
And the second part is actually trivial because of definition of V star T01.
Can you check that it's not this V is not the one you wrote below on the right?
I'm bad with my lesson rates. This here?
No, far below. This one. It's not the same.
Oh.
Okay.
But then we just flip.
No, it's not again.
Oh.
No, the left.
It should be star 10, right?
So
Here?
this one, check up in, it doesn't correspond to L, the one you just, no, not this one, below. This one, check L,
Check L?
now.
Oh, I see what you're saying. Thank you. So this should be 0, 1.
Okay,
Yeah.
okay, so now I understand the point of this. Thank you.
There we go. Is this, wait, okay.
Okay,
Yeah, I need to look at the definition again.
Okay,
Yeah, okay.
perfect. Thank you.
And this, I think, is the apex of the complexity or the complications for today. Then we're going to look at the algebroids.
There are two letters rho. Are they the same here and upper?
No, they're different. Because in both, I mean, so rho is just an element of, so I'm thinking of rho as an element of the exterior algebra of, so this is like, oh, okay, we can use a different way. Let's use alpha. They're the same kinds of things, but they're not the same, element.
Okay.
Okay. Okay, are there any more questions about this material? So, my impression, or my expectation, is that this, is that here we're or because of this example, I think we're generalizing from, this related material of complex geometry. So that's how I think this is going to come back. For example, we can get like decompositions of forms in terms of like, so in the pure complex, not generalized complex, but classical complex setting, like the different levels of like holomorphic, anti-holomorphic forms and stuff. I think that might be the connection. Okay. So that was 2/3 of the. Let's talk about Lie algebroids. And actually, maybe we'll just do Lie algebroids and not the related foliation material, and that should be a good amount of stuff. Okay. So I'm gonna.
Also, one comment, how to relate it to physics, which always puzzled me. But anyway, so you have a manifold, and then you have a spinor bundle, which, at every point you have a spinor. Then a section of the bundle is called a particle. Like fermions, bosons.
I think, yeah, this is also that they call the.
Берете многообразие, дальше в каждой точке вешается такой спиннер. Дальше для каждой точки выбираете какой-то спиннер определенным образом. Вот тот выбор всего это называется частица. То есть там фермион это вот какая-то такая страшная хрень. Что бы это ни значило. Yeah, sorry.
I think it's representing a field, like a physical field. But one thing that confused me with that material is that I think they call a section of the spinner bundle a spinner. Also, in addition to an element like so it would be as if we call a vector field and a vector both vectors, and so that confused me. I think maybe I'm wrong about that actually.
Yes, no, because you always call a tensor vector field also a tensor, right? Consider tensor somewhere.
Yeah.
Frequently it means you consider tensor vector field. Vector field. And then the difference between quarks, muons, and leptons is a different spinor space you take.
I think that only humans are spinners.
Yes, yeah, but okay, I don't know the difference between muons, muons, and so on, especially from the point of view of spinners. So you do understand this difference?
So I know that with bosons, when you describe bosons, you should choose you should choose fields like tensor. Tensor.
And here you take the exterior power.
No, it all depends on the representation of Lorentz group. And
What?
of the Lorentz group. It's two properties of SU2. No, when you say about an algebra, and they are described by two semi-integer numbers, and spinors are those which transform by representations with the semi-integer, and bosons are those that transform by integer. Maybe it's not true, but a little about. So, and when it's semi-integer, it's
Just open and consider aloud.
Oh my gosh.
They have this classification of strange quark, bottom quark, and so on. Also, how related are spinners. But
just get specificated in similarity.
All right. Okay. So let's talk about Lie algebroids now. And this is going to be very visual and very nice. And so this discussion will have two parts. First, we're going to talk about real Lie algebroids. But in this course, we don't really care that much about real Lie algebroids. We mostly care about complex Lie algebroids, which we'll talk about second. And when I say talk about, we're basically just going to give lots of examples. And if you've seen this material before, then it will probably look pretty familiar because the examples always seem to be the same ones. Okay, so 2. Algebroids. Okay. So definition. We'll just start with the definition and give a whole bunch of examples. A real Lie algebroid on M, so M is a manifold, smooth manifold, consists of 1, so three components. First, a real vector bundle consists of a real vector bundle L over N. And here, throughout this discussion, I'm going to follow the conventions used in Gualtieri's thesis. As far as what I'm calling, denoting of the algebras. 2, a Lie bracket on the space of sections of L. So we'll denote that C infinity L. And third, an anchor map. A from L to the tangent bundle on M, and this is a smooth bundle map. Okay, so I always like to have some sort of picture when a new definition comes up. So here's what I have here. Let's see, so here's our manifold M. A Lie algebroid is a vector bundle over M, L, vector bundle projection pi. And it comes with, so I'm not going to write the brackets. Oh, there's some conditions. But first I'm going to draw this stuff here. So here's X, here's a fiber of L, Lx, and then the anchor map A maps elements from the fiber of L at X to the fiber of the tangent bundle, or to the tangent space of M at X. And so when I had first encountered this idea, I thought, oh, well, that sounds very much like something that's induced by the projection. But just as a very quick remark, note that A is mapping from L to X. Well, pi star would map from TL, say V to TXM. So to me, it sort of seems like this is first order data here. It's directions and magnitudes on the space, and this a priori I would have thought of as like 0th order information here. But let's see. So okay, so there are two compatibility there are two conditions that we need to put on these constructions on this data. So such that first, the anchor map applied to the bracket, or the Lie bracket of two sections X and Y needs to be equal to so this is in L, this is in, these are vector fields on M. So this is just saying that A induces a Lie algebra homomorphism. From sections of L to vector fields on M. So that's the first condition. The second condition, oh, and how I sort of thought of this is it feels like we're extending the, not necessarily, but this felt sort of like we're extending the vector fields, but that's not necessarily maybe how to see it. The second condition is that we have that if we take the Lie bracket between x and f of f times y, that this is f times xy plus the anchor applied to x times, or then that's, so this is a vector field, we apply it to f, and that is scale, and that scales y. So this is a Leibniz rule. For the brackets. I think we can also see this as a compatibility condition between the
Just a second, so it's I see the first summand. The second summand is what is you take by the anchor the x to the tangent vector field.
Yeah,
and then
yeah,
you
we
can
push
shift
down
a
x.
f along it. You have a function, and
Yeah.
you just multiply y by this function, right? What is it?
So yeah, we take the we apply the vector field ax to f, that gives us another function, and then we scale y pointwise by the values of that function. Okay, so let's see. So these are the so these are all the definitions that we have for this. And then I think we'll just look at examples for the next 15 minutes. Are there any questions about the definitions or the characterization? All right, then examples. So first, maybe the easiest example is we take a okay, yeah, we can take a Lie algebra G and a point, the anchor map is 0. And the brackets are just the Lie brackets on G. So in this sense, we might think of a Lie algebroid as a as a generalization of the notion of a Lie algebra. Second example.
Sorry about the first example. What is G? Can you repeat?
Oh, G is a Lie algebra, any Lie algebra, and we're considering a point as a zero-dimensional manifold.
Okay.
Second example is the tangent bundle on M. So that looks like this. So tangent bundle on M with the anchor map just the identity. And the brackets just the canonical Lie bracket on the space of vector fields. So here is the picture. Then a closely related example is if we take not the entire tangent bundle, but an integrable subbundle. Here. So F to M integrable subbundle of the tangent bundle. In this case, the anchor map A is the inclusion of our subbundle into the tangent bundle. So here's something like this. X. A is inclusion. And here's the fiber of F at X. And then one last example. Here. Slightly more complicated example. This is the Tia algebroid. Which takes a principal G bundle P acted on by a Lie group G over M. So should I clarify what a G principal bundle is, or is this okay? Great. So we start with a G principal bundle over M.
Can you remind me, please?
Yes, okay. So a G principal bundle is it's a fiber bundle over M with which comes as indicated here, P over M. This is the bundle part, and it has a very special property. It comes with an action of the Lie group G. Such that the orbits of G in P correspond precisely by the bundle projections to the points of M. A picture. So here is M, here is P, here is G, which will just be S1 because we can draw it. G here in this case is acting on P by rotations. Here's X. Here's the fiber of P over X. Then the orbit And it needs to be free, a free action. So the orbits of P are like copies of the Lie group, but they don't come with a natural multiplication. Let me see. Yeah. So maybe a more technical definition is that a G principal bundle over M is a space, or so is a fiber bundle P with the property that G acts freely and transitively on, or freely on P and transitively on the fibers of P.
You also can say that it's just a bundle with fiber G, such that locally in each chart there is some trivialization, that the action is just multiplication by G.
That's
No chart like U cross G, and the action of G is just multiplication by the second coordinate.
But there isn't a canonical identification between. Yeah. But and then just to add to that, as a remark, that though there isn't a canonical identification between the elements of the fiber and the points of G. Okay, so then the T algebroid. We have a short exact sequence. Zero and P at P. So this is the T algebroid. Oops. Like this. Tm, this is our anchor map, 0. Okay, so this is the adjoint bundle associated to the principal bundle P, so its definition is the representation, or fiber product of P with the Lie algebra G. So, and this is just defined to be cross G mod G, where we act by the adjoint action on the Lie algebra of G and the inherent action, the given action of G on P. I'll say something about this in a second. The T algebroid then as a set, or as a space, is TP mod G. So G acts on P. That action extends to the tangent bundle of P. And then this is just the tangent bundle of M. So, I want to explain this, explain what I read. So the adjoint bundle of P, we can understand it possibly as the vertical tangent bundle of a generic point of generic points of the fiber of P. And then also to remark, these are bundles, each of these are bundles over M, not bundles over P. So we can think of an element of the adjoint, of the little adjoint, because there's also a big adjoint, just like there are little and big adjoint representations. An element of this bundle is can be thought of a G, okay. These are sort of, we don't have a canonical point which to pick in the fiber because this is over X, But if we choose a vertical tangent vector somewhere, then we can translate it to other points. So how I typically think of the little adjoint bundle is as sort of a generic or a vertical tangent fiber to a generic point on the fiber of P above X. Yes.
And
There's
do
another way.
you know if this is the kernel of the push forward
Of
by the projection?
The vertical, the answer to that is no for a technical sense, in that the elements of the adjoint bundle don't live, they're not literally tangent vectors. The vertical tangent vectors here are, of course, those that lie in the kernel of the push forward. But the idea, so the idea sort of is that here is the Lie algebra. That Lie algebra gets identified at every point here. So G, oops. G at P, where P is a point in the fiber. And those are representing the vertical directions. Those are representing the directions that G can take you, and so that is the orbits of G. But those orbits coincide with the fibers of P above M. Okay, so yeah.
So is it isomorphic to the vertical tangent vectors?
Well, but the vertical tangent bundle is a bundle on P. So that's why I'm saying it's a little bit heuristic, because I'm saying that you can pick any point up here. I believe it is actually you can think of it as a vector field, a G invariant vector field on like a group G invariant vector field on the fiber. But maybe more properly, the way to think about the little adjoint bundle is it's the infinitesimal transformations of the fiber, and transformations of the fiber in that it's preserving the G principal bundle structure of P. That I think is like the true way of thinking about it. Okay, so then the Atiyah algebroid here, well, this is like generic, not generic vertical tangent vectors, but just generic tangent vectors above a particular point. So here's Y. Here's the fiber of P above Y. Here's P. Tangent space. We can think of an element of the Atiyah algebroid X as an element of the tangent the tangent space here at P, but we can translate by G to any other point. And then the anchor map, and so the anchor map, so these are horizontal components, in quotes. Is registering, it's telling us what is the horizontal component of this generic tangent vector in P.
Because when you translate in the Atiyah algebroid, when you translate in the fiber, you doesn't change the horizontal component. When you translate with the G action of G.
It shouldn't. It won't when. It certainly won't when G is abelian. I don't think it should when. I think no. Yeah.
So the idea of the Atiyah algebroid is to take the vector fields on P, but only those that are, say, we identify those which are translated under the action of G.
Only those which are, or we consider those tangent vector fields along the fibers, because they don't have to be tangent to the fibers. They're not tangent vectors on. They're not tangent vector fields on the. They're not G invariant tangent vectors on the fiber. That is the adjoint bundle. They're tangent vector fields of P, but defined only along the fiber, so they can point off of. Yeah, they can point off the fiber. Which are G invariant. And because they're G invariant, we can push them down to a well-defined element.
So is it kind of a way, as we define the algebras as left invariant vector fields? Is it similar?
Maybe, I haven't thought about that. That's interesting. That's worth following up with.
I just realized that.
Yeah, maybe actually. Okay, so that's then what the anchor map does. It takes the horizontal component, or it registers that component. And then the Lie bracket of sections is just inherited from the Lie bracket of vector fields, the standard Lie bracket of vector fields on P. And that is it for what I have to say for today. Are there any questions about this? So I'll also add that when I said that, I think the correct way of thinking about the adjoint bundle to P is as the infinitesimal transformations, or structure preserving transformations of the principal bundle, and that's because this is the infinitesimal version of the big adjoint bundle, the sections of which are known in physics, I guess, as the gauge group. And the gauge group then gives us the transformations, the non-infinitesimal transformations of P. All right. So yeah, are there any questions about this material?
I have a technical question.
Yeah.
Where do we have the recordings of the seminar? Because next time I'm not here,
Oh,
so I'd like to watch it.
I can put it on YouTube, or I mean, I because it just gets automatically uploaded to Zoom. Actually, I'll send you the Zoom link.
Okay.
Great. Okay. Well, if there are no questions, then I'll see hopefully everyone next week.